Optimum control settings for PID controller. Another method of tuning is continuous cycling method or closed loop method. The another name for this is closed loop method. Sustained oscillation method. Another name is sustained oscillation method. Closed loop method, continuous cycling method, or sustained oscillation method. In this case, this is applicable only for fast process. It is applicable only for fast process. And by simulation. Simulation also we can do this way. By simulation also we can do, whether it is fast or slow, simulation means you can do this method. Otherwise it should be fast. We can do for any process. Sustained oscillation method can be done for any process. But the problem is if the time constant is very large, for one cycle it may take here minutes together. In some industries it may take hours together for one cycle. In one cycle we cannot say that it is sustained oscillation. So 2-3 cycles we have to see whether amplitude is constant or not. During that time, no disturbance should enter the process. It's very difficult to keep disturbance free for that long time. That's why continuous cycling method can only be applicable to small time constant process only. That is flow process. In the flow process, we have to put the process in closed loop. Put the controller only P only mode. Put the controller in P only mode. Put the controller in P only mode. Bring the process. First step is bring the process to nominal operating point. Then put the process in closed loop. So in manual mode, we bring the process to nominal operating point. Then we are doing the bumpless transfer and put the process in closed loop. Third point is gradually increase the gain till it exhibits sustained oscillation. We know that as gain increases, it is not a first order. If it is a first order process, as gain increases, the pole will move away from j omega axis. If it is pure first order, but it is not so in practice. Of course, the flow process, mathematically, it is a zero order process. But in a flow process, what and all in series with that? In our lab, if you consider, the first one is it has a controller. It has controller. This is the controller. Controller. The output of the controller is given to VFD, because this 420 milliamps is given as input to VFD. Output of the VFD drives induction motor. Induction motor in turn drives the pump. The pump in turn gives the flow rate. The flow rate is measured by differential pressure transmitter, and it is given as in feedback to the process, feedback to the controller. This DPT is output of the DPT is given as feedback to the controller. How many components involved here? Controller 1, VFD 2, induction motor 3, pump 4, process 5. Even though it is zero order, mathematically, maybe at least first order. This measuring device, RFIs meter, and RFIs meter cascaded with the DFT, DPT, differential pressure transmitter. 1, 2, 3, 4, 5, 6 are in the loop. 6 are in the loop. At least sixth order. That's why even then it is very fast. Even then it is very fast. The process is very fast. That's why we can go for continuous cycling method. Because it is not first order. That's why if you from third order onwards, if you increase the gain, what happens in root locus we have seen. Third order onwards, let us assume that all the poles are on the negative real axis. If you increase gain, the poles will move towards j omega axis. From third order onwards, it is sixth order. That's why definitely the poles will move towards j omega axis. So gradually increase the gain till it exhibits sustained oscillation. Definitely it will exhibit sustained oscillation because order is 6. So at one point, the poles will be on exactly on the j omega axis. The poles will be exactly on the j omega axis. This is S plane. Sigma j omega, S plane. The poles will be on the j omega axis. That time, the process will exhibit a sustained oscillation. It will exhibit a sustained oscillation. Like this, it will exhibit. The amplitude will be constant. Amplitude will be constant. That time, we have to note down, exhibit sustained oscillation. That time, note down Kc, that is equal to K max. That time, note down the Kc, that is equal to K max, the ultimate gain or maximum gain. Ultimate gain or maximum gain at which the system exhibits sustained oscillation. Not Kc, K max. That Kc equal which exhibits sustained oscillation, that Kc is K max. We got K max because the present value of Kc gives sustained oscillation. That's why it is not Kc, it is K max. Ultimate gain. We got ultimate gain. Now, we have to find the period of oscillation. This is the period of oscillation. To find the period of oscillation, here, no valve is involved. If valve is involved, the valve stem will go up and down. Valve opens 100% means goes up. 100% closed means completely come down. The valve stem will go up and down. From that, we can see how many oscillations we can note down. But here, we are not using valve. The final control element here used is VFD. That's why there is no valve. That's why the oscillation, we have to see the trend otherwise. Trend means, it is also a technical word used in industries. Trend means, if you plot this on a graph sheet or monitor, the process variable. If you plot this, it will be looking like this. Am I correct? It is oscillating, you know. That's why it is looking like this. This is called a trend. If you are able to see the trend in the monitor, means there you can measure the time. If it is not possible, if it is not so, means we have to measure the period of oscillation by some other means. For that, in the flow tube, a rotameter is connected, local indicator. Rotameter is, what is the purpose of rotameter is, it is a local indicator. Local indicator. Rotameter is local indicator. Local indicator. That rotameter, bob in the rotameter, this is the bob. In the rotameter, it will go up and down. It should go to a particular value up and particularly down, it should come. That is called sustained oscillation. If the amplitude is constant, then it will go to one particular value in the top side and particular value in the downside. Again and again it should go. Then only it is called sustained oscillation. So for a sustained oscillation, we have to note down for 10 oscillations. Because if you find the time for one oscillation, it may not be correct. That's why find oscillations for, find time taken for 10 oscillations. Then divide that by 10, you will get time for one oscillation. Divide the time t divided by 10, you will get TU, ultimate period. Ultimate period equal to t by 10. Ultimate period. Ultimate period you will get. These are the two parameters, process parameters required. K max and TU. If you know these two, you can find the tuning parameter by using Ziegler-Nichols. The Ziegler-Nichols tuning parameters. For P controller, Kc equal to K max multiplied by 0.5. If it is in PB, in the lab, it is in PB. What is the relation between PB and Kc? 100 by Kc, or Kc equal to 100 by PB. So if it is PB, means if it decrease, then Kc will increase. In that case, you have to divide by 0.5. PB means. So 0.5 times K max is Kc. That is for P only controller. For P plus I controller, Kc equal to 0.45 times. 0.45 times K max. We have to reduce because of introduction of integral mode, there is a threat to the stability. That's why we are decreasing by 0.45 times K max, Kc. And Ti equal to Tu, ultimate period divided by 1 point. Thumb rule suggested by Ziegler-Nichols. Then the tuning parameter for PID mode is Kc equal to 0.6 times. We introduced derivative mode. That's why there is a improvement in the stability. That's why the improvement in the gain margin. That's why we are multiplying by 0.6 times K max. And Ti equal to Tu by 2 and Td equal to Tu upon 8. These are the tuning rules for continuous cycling method. Tuning rules are optimum controller settings. This is called optimum controller settings. In both ways, it can be asked. Optimum controller settings. So we got by Ziegler-Nichols method. Here, one thing we have to note down here. What is the maximum opening for the valve? 100%. If you any increase in controller gain beyond Kmax, will it open above 100%? No. It will not open beyond 100%, but the controller output will be more than 100%. That's why if you increase beyond Kmax, if you increase the gain beyond Kmax, what will happen is it will exhibit limit cycle. It will exhibit limit cycle. This is not in theory, I didn't tell. This is called a limit cycle. A limit cycle is a nonlinear behavior. Nonlinear behavior. Limit cycle means what will happen? If it is the valve can open more than 100% means it will open no limit cycle. But valve can open only 100% means it cannot open beyond 100% means it will go to maximum value and stay for some times. This can be noted in the bob. If any increase in Kmax, K further beyond Kmax, this rotameter bob will go and stay there for some times, then come down. It will come to bottom and stay for some times, then go up. That is called a limit cycle behavior. If you plot the response, the trend for this, it will be like this. It is sustained oscillation means it will be like this. Sustained oscillation means like this. Limit cycle means it will be like this. It stay for some time, then come down. Stay in the bottom for some time, then go up. This is limit cycle behavior. This is sustained oscillation. This is called a sustained oscillation. The bottom is called limit cycle behavior. If you draw the trend, it will be looking like this. We should not increase Kmax beyond a certain value. In the lab also, you should not decrease the PB beyond PB min. PB max means, Kc max means 100 by PB min. If you decrease further, if you decrease further, it will be in limit cycle. That's why you have to ensure that the rotameter bob should not stay in the top or bottom while doing experiment. Otherwise, you will get a wrong value of Kmax, wrong value of PB min, Kmax or PB min. So we should ensure that it is not limit cycle. We should ensure that it's not a limit cycle behavior. That's all about the tuning of PID controller using continuous cycling method.